Okay, I hope everyone can see my slides and hear me. So, great pleasure to talk to you this evening. I was doing a little calculation, and it's almost exactly 40 years since I was sitting my finals exams for my degree in physics. And it's very interesting to note that in that 40 years, a great deal has happened in the subject area of quantum physics. And so, if you know about the history of quantum physics, then in fact, it started its development in the early part of the last century with the work of Einstein and Planck, and then Max Born and Schrödinger and Heisenberg and Dirac and many more. So the quantum physics that I was taught was all developed rather earlier than that, and the fundamental features of quantum physics that I'll briefly mention in just a minute were all known and understood. But there have been two major developments really in the last 40 years since I finished my physics degree, and those two things are firstly that in terms of being able to do experiments and manipulate quantum things. 40 years ago, people could generally do experiments with collections of quantum things and manipulate them around. And over the last 40 years, what they've now been able to do is isolate individual quantum things and control them and manipulate them, or a small number of them. So they can now, in laboratories all over the world, do fantastic experiments where they control quantum systems. So that's been one big jump forward. The other big jump is that we've learned that there are new technologies that can now be built on these very fundamental features of quantum physics, and that's what I'm going to be talking about. So if I can get my slides to move forward. So that's the purpose of my talk, to try and explain a little bit about these new technologies. So as I say, 40 odd years ago, when I was learning about quantum physics, the fundamental features were all understood, but they were regarded as things that didn't impact everyday life. They were things you needed to understand to do experiments in laboratories somewhere, but they weren't something that could have any impact on people everywhere. But we now know that is all different. And in fact, there are whole new technologies now that are underpinned by these basic fundamental features of quantum physics, the things that make it different from everyday life and classical physics, and if you like, your intuition. And so I've named these things with their proper words. So there's three features of quantum physics that make it counterintuitive, and those three things I'll explain in a little more in just a minute. And they are the idea of superposition, the idea of entanglement, and the idea that you disturb things when you measure them. And so we'll see how these can underpin new technologies. And the really interesting thing about these new technologies is because they're built on something different, they have new abilities, and they have the potential to outperform the familiar information technology that we all use today. And so the first of these that I'll mention is really computing. And so in quantum mechanics, things can be in superposition. And what that means is that they can be in many different states at the same time. And so if I wave my hands and say, suppose you had a computer chip that worked according to the laws of quantum mechanics, that computer could operate and do many calculations all at the same time in the same device. So it's like parallel processing, but all those parallel processes are all in the same physical quantum system. If you can do that, if you can do many calculations at the same time, then if you can manipulate all of those calculations together, you can do something which is far more efficient than you can do with an ordinary computer. You can do calculations that are simply beyond any form of computer that we have currently, and the applications that you can achieve. You can simulate and model things far better. You can do cryptanalysis. You can break codes, and I'll say a little more about that in a minute. You can search more efficiently through databases. There are all sorts of algorithms, if you like, that you could run on a quantum machine. What do you make these things from? Well, there's a whole lot of candidates being considered for this. There are certainly superconducting devices. Some of you may have heard that both Google and IBM, big computer companies, are building machines based on superconductivity. People are trying to track tiny ions or atoms, individual atoms, and use those as the building blocks of a quantum computer. They're trying to use light, and they're trying to use semiconductors and little defects in diamond and all sorts. So there's various candidates for what people are trying to build these machines from. But we know if we can build them, we can achieve computations that we can't do by ordinary means. So that's the idea of superposition, many states. The next thing I want to mention is the idea of entanglement. So entanglement is where quantum systems such as atoms or quanta of light called photons can be intimately correlated in a way that's much, much stronger than any correlations you can imagine in the real world. So these quantum systems can be linked, and this can be over a significant distance, and they can have a correlation between them, which is actually stronger than any kind of conventional correlation. Now, what that means is if you have a couple of these quantum particles that are correlated, and you bounce one off some object that you wish to image or detect in some way, and then you bring these two particles back together, you can actually learn something about the object with more detail or with more precision than you can learn if you use the same sorts of atoms or light in a conventional state. So you can actually use, as I mentioned, light atoms. You can also use tiny little vibrational nanomechanical devices or something if you want to detect fields such as gravity with greater precision. So there are various systems that you can use in an entangled state or other interesting quantum states, which enable you to probe systems more accurately. So one example of this, you may well have heard of the detection of gravitational waves that was achieved at the LIGO detector a couple of years back. Well, they're now upgrading the LIGO detector to actually build quantum versions of it. So they're actually using squeezed light in the LIGO detector in order to improve the sensitivity of detecting gravitational waves. So that's one example of quantum sensing based on interesting quantum states of systems. The third fundamental feature of quantum physics is the fact that when you measure quantum systems, you disturb them. So if you have a quantum system and you wish to learn about it, the only way you can do that is to come along and measure it. And when you do that, you will disturb it. And that disturbance is fundamental in that it's built into quantum physics. It's not that the people who do the experiments will work out in a few years' time how to do the experiment better, and they will get round this fundamental disturbance. It's actually an intrinsic part of quantum physics. It's needed, in fact, to make quantum physics consistent with Einstein's theory of relativity. So it's not going to go away. And it is very useful from the perspective of doing secure communications, because if people, and they're always called Alice, who sends stuff to Bob, if Alice sends quantum things to Bob and someone has a cheeky look in the middle, then by having that cheeky look, they will inevitably disturb some of the stuff that Alice is sending to Bob, which means that Alice and Bob can work out that someone is trying to eavesdrop. So you can build a secure communication system on the basis that quantum things get disturbed when people measure them. And in terms of what we use to do quantum communications, then it's light. We use quantum signals of light to establish secure communications. And this may be carried down optical fibers, the kind of things that carry conventional high-speed communications now, or it may be through free space. And I'll mention a little about both of those options later on. So just to give you a bit of perspective, I mentioned that building a computer that works according to quantum laws would enable better cryptanalysis. And in fact, it's a bit more serious than that. In fact, if someone builds a big quantum computer, which would have to be very much bigger than the one that Google, for example, is currently operating, if someone can build a very big one, then they could break most of the public key encryption that is currently used for our secure internet. communications and so on. So a significant problem is looming if quantum computers really are developed in the future at that kind of size. So that's one thing that's worrying, the fact that the quantum computers will break a lot of the current cryptography that we're using. Another serious consideration is, I just mentioned, quantum sensing and imaging will enable us to detect things, beyond what we can currently do. The good news is that despite both of those things, which you might think of as problems, then there are new ways of doing secure communications based on Alice sending quantum things to Bob, which are immune to both of these potential attacks, if you like. So although we know problems are looming, we also know that solutions are looming, which is very good. And in addition to quantum-based secure communications, it's also the case that these things that will be broken by a quantum computer, people are also trying to work out new forms of mathematical crypto that we hope are immune to being broken by a quantum computer. And so despite these worries, we think there is a nice way forward for secure communications in the future. So people are investing in this worldwide. In fact, many countries or the EU and so on have active programs. And in the UK, we have a very substantial program. And I'm going to tell you a little bit about that. So we kind of have a bit of a tradition in the UK of dropping the ball when it comes of turning basic science into technology. So we have a long history in the UK of doing fantastic basic science, but then very often that has turned into technology elsewhere in the world. But over about the last 20 years, successive UK governments have realized that not only should we invest in the basic science, but we should also make sure that we turn that into working technology. And so quite a number of subject areas, graphene included, for example, have benefited from investment trying to turn the basic science into technology. And our turn, if you like, in the quantum regime came in 2013. So at the end of 2013, George Osborne, who was at the time the Chancellor of a coalition government, found £270 million to start a new UK quantum technologies program. And that program started about a year later at the end of 2014. But this very large investment was to make sure that all of the basic quantum science that had been done could actually turn into these potential technologies. So in the UK, very substantial investment was made in four great big projects. And I'm going to tell you a little more detail about just one of those in a minute. But there was investment in these four large projects to actually build the technologies. There was investment in training and skills and all sorts of other things. So there was a very substantial investment. And this was initially a 5-year program. So it started late 2014 and finished towards the end of last year. And it's been renewed for another 5 years. So I'm going to give you in a minute a quick snapshot of what we've done in one of these technology hubs over the last 5 years, and then a quick forward look on what we're going to be doing in the next 5 years. And so these four hubs that were set up in the UK kind of covered all of the technologies that I've just tried to outline. So there was a hub established to work on quantum computing, and that's led by the University of Oxford. But in general, these hubs have about 10 different universities involved, plus many companies, and I'll show you all of the folk involved in our hub in just a minute. But so each of these hubs is a big, substantial, spread out collaboration in across the UK. And so the one led by the University of Oxford has been focusing on building quantum computers of various sorts. There's one led from the University of Glasgow that focuses on using light for quantum enhanced imaging of various things. There is the hub led by the University of Birmingham, and they use atoms to sense gravity and so on to find buried infrastructure and things like that. You can build gravitational-based sensors that can pick out buried things more accurately than you can do otherwise. And then there's a hub that's built on realizing secure communications, and that's the one that I lead. And so this is what we said we were going to do in the last 5 years, and I'll tell you what we've achieved in just a minute. So our aim was to take basic science and to push it and to develop new technologies that can actually achieve secure quantum communications in a practical way. And the biggest thing that we do, and I'm not going to explain in detail how it works, but I will talk just a little bit about it, is quantum key distribution. And so this is when Alice and Bob communicate with each other. And after they've managed to communicate quantumly, they can share a key between themselves. And that key can be used to encrypt subsequent communications and protect them against eavesdroppers. So in our hub in the last 5 years, we got about a tenth of that £270 million. And going forward for the next 5 years, we've got a similar sized budget. And in fact, going forward into the next 5 years, because UK industry is now beginning to also invest in these various quantum technologies, then in total, the estimated budget that includes all the industrial contributions over the whole 10-year period is going to be about £1 billion. So it's a very substantial investment. So before I tell you just a little bit about what we have done and what we will be doing, I'll just say a little more about key distribution, which, if you like, is the integral building block that we use for quantum communications. And it's important to understand the distinction between sharing out of keys that can be used for encryption and then the use of the keys themselves. Because the way it works is that Alice and Bob can share out quantum systems and measure them and establish a key and work out whether anyone else knows anything about that key. And that's the quantum part. So Alice and Bob need to send quantum signals between each other to do that. And as I've said, this could be through optical fiber, it could be through free space. And both of these are options, and it depends on what length scales you're communicating over as to which of those you do. And I'll come back to that in just a moment. But the important thing to note is that once the communications have been done to establish the keys, you can then use these keys for whatever you like. You can use them to protect information. You can use them for transactions over the internet. So the use of the keys once they've been distributed is not quantum. So you don't need the quantum technology to use them. You just need the quantum technology to establish the keys. And the important thing about keys, which are almost certainly true for all secure communications, is that they're a consumable. You use them once and then you should delete them. If you use them again, you'll probably violate the security, and people will be able to subsequently decrypt your encrypted information. So in addition to establishing quantum keys, when you want to top them up, that's when you also need the quantum technology. So that's key distribution. This, as I said, I promised you I'd show you a typical. So each of the 4 technology hubs that works in the different technology sectors will have a slide like this. It shows all the various university partners, but also it shows all of the companies that work with them. So of course, in the communications domain, British Telecom obviously handle a lot of the communications in the UK, and so they're a partner with us, and we even have a working network with them now. So there's BT, who, if you like, are a service provider. There's all sorts of technology providers and so on, and people who will use secure communications in the future. So that is the slide showing all of our partners. As I say, it's a big distributed collaboration with about 10 universities and all of these industrial partners. So what have we done over the last 5 years? Just to show you that this is real stuff now. It's not just hypothetical now. It really has moved out of the laboratory and into the real world. So one of the things we've developed, and we have a prototype that maybe doesn't quite look as sexy as this picture here, but it's getting there. I said you can either communicate through free space or over optical fibers. And over very short distances, it's clearly convenient to communicate from a handheld device to some other device through free space. And so we've developed a very short range quantum key distribution system that can work between a handheld device, such as a phone, and some device in the wall, some receiver. So the Bob unit would be a receiver built in the wall. And you can share quantum keys between your personal device and it might be your bank, it might be your employer, it might be your university or whatever. You can share keys between yourself and all of these institutions. And then, as I said, you can use these keys subsequently for various transactions. So short range, you can share quantum keys over free space. On a longer distance, you can share keys down optical fibers. And here is the sort of test network that we've established in the UK. There's a network that now goes around Cambridge. There's a network that goes around Bristol, and we're borrowing pieces of optical fiber to go between Cambridge and Bristol as well. There's also a network which is shown as a dotted line here that runs from Cambridge to British Telecom's R&D centre at Adastral Park near Ipswich. And we now have a working network there between our hub partner Cambridge and BT. And so we're using that to demonstrate applications of secure quantum communications along there. We've also built stuff on chip. University of Bristol, our partner there, showed the world's first chip-to-chip quantum key distribution demonstration. They published that a couple of years ago, so that is now working. And we're now developing what we would call next generation technologies beyond QKD. I've already mentioned we work very strongly with industry. We have many industrial partners, and they've been essential to getting the work done over the last 5 years. But also now, as part of the phase 2, which is going to run for the next 5 years, the government is now, so ISCF stands for Industrial Strategy Challenge Funding. And so the government, as well as funding people in universities to work on if you like, taking the basic science and turning it into working technology, they're now supporting businesses and universities as part of these projects as well to really make it commercializable technology. So there are many parallel projects that are now going forward in phase 2 to commercialize this new technology. So that's what we've achieved in the last 5 years. I'm not going to talk you through the intimate detail of all of this in the next 5 years, but we're basically continuing to push our work forward, for example, on the fiber-based network that is going around the UK, and we're hoping to expand that out. We're going to continue our work on the short-range handheld QKD. But the one thing I would like to highlight that we're going to be doing over the next 5 years, which experiments are already underway elsewhere in the world and have shown that this is feasible, even if it sounds really rather difficult. You can do quantum key distribution between something on the ground and a satellite that is orbiting around the Earth, or possibly some kind of high altitude platform that's between satellite level and the ground. And so that's one big thing that we're adding to our agenda for the next 5 years. We want to do an experiment to demonstrate that we can exchange quantum keys between a small satellite about this sort of size and a receiver on the ground. So we're pushing forward over the next 5 years with very many new activities in quantum communications. And I'll just mention standards as well, because standards are something that always are needed for new technology. So when new technologies emerge, in order that the different pieces of new technology can work with each other, and in order to ensure that everything fits together, then standards are very important. So alongside developing the technology, it's very important to develop the relevant standards. Okay. Just to show you that this really is here now, then okay, this is not quantum communication. This is a first small step in that you can, as well as communicate quantumly, you can actually use quantum devices to generate random numbers, which are very important to underpin cryptography. So as of last month, there's going to be a new version of the Galaxy smartphone that will actually contain a little quantum random number generator. So soon you will actually be able to buy quantum technology like this and carry it around in your pocket. So that's how real it is now. So I'm going to close and just leave this slide up for a minute. If people are interested in learning a bit more about this, then there's a whole website for the whole UK national programme, which includes all 4 of those hubs and various other activities. If you're interested in particular in quantum communications, you can read about our stuff. And if you're interested in reading about all of the quantum technologies in a nice sort of low-level article that was written for government, then you can read the Blackett Review on quantum technologies that was published just a couple of years ago. So with that, I'm going to say thank you very much, and I'm going to stop sharing my screen now, but we can put it back up if people want, and we'll take questions. So thank you very much.